This lecture will be a quick summary of what I cover in the Chapter 10 States of Matter notes in first year chemistry. The first thing that we talk about is the kinetic theory. It's a way to describe the motion of particles, and we've learned in previous chapters that in solids, liquids, and gases the particles move differently. In a solid they vibrate in fixed positions, and in a liquid they kind of slide over each other in clumps, and in gases they fly around as individual particles, as you can see in the picture below. So the kinetic theory is a way to describe the motion of these particles, and we make some assumptions about how the particles are moving in a gas. So this particular chapter we're going to just specifically look at how the particles are moving in a gas. We first assume that in a gas the particles are very, very tiny. They happen to be individual particles. Now they could be individual atoms flying around, or they could be molecules flying around. And the second assumption that we make about these particles as they're moving, they move in straight lines, and then they are assumed to collide with each other. And then in the third assumption that we have on the slide, when the particles do collide, the kinetic energy is conserved. Now the kinetic energy is the energy of their motion, so if they're moving faster they have more kinetic energy. And so we say that the kinetic energy during these collisions is called perfectly elastic. And what that means is they bounce off and they don't lose any energy. So if one particle were to slow down when it collides, another particle would have to speed up, so the total amount of energy is conserved. And this is the kinetic energy that we're talking about that's conserved. So when gas particles collide, their kinetic energy is conserved. Now if you played pool with a gas particle or a pool ball that was perfectly elastic, they would never stop bouncing around the pool table. We know that in reality actual particles do slow down, actual pool balls do slow down and stop. But in gas particle collisions, whether they collide with a person or another gas particle or with a wall, they're going to bounce off and not lose kinetic energy. So the last picture on the slide shows a ball bouncing and losing height as it bounces, and that would not be a perfectly elastic collision. If you had a perfect elastic collision, the height would always be the same no matter how many times it bounces. On the next slide we talk about how temperature affects the kinetic energy of a gas particle, and as the temperature gets higher and higher the particles are going to move faster, and so they're going to have more kinetic energy of motion. And this is called a direct relationship, which means as one variable increases another variable would increase, and in this case as the temperature goes up the kinetic energy would go up. And this is also known as a linear relationship in math class, and so that's why the graph shows a straight line. Now at 0 degrees Kelvin there isn't any kinetic energy in the molecule. Another name for 0 Kelvin is absolute zero. So if you didn't have any temperature, you wouldn't have any kinetic energy. Now if you wanted to double the Kelvin temperature, that would double the kinetic energy. So when I tell the students that something is twice as hot, I'm saying that it has twice the Kelvin temperature, or it would have twice the average kinetic energy. So kinetic energy and Kelvin temperature are synonymous with each other in this particular lesson. Now, I tell the students that if you want to prove to somebody that gas particles do conserve kinetic energy when they collide, a proof of that would be that the room isn't slowly getting colder. As the particles collide with each other, it's not like they're slowing down, which means the room would get colder and colder and colder. Because they're perfectly elastic, they don't lose this kinetic energy, and so the room stays at an average normal temperature without getting colder as the collisions occur. On the next slide we do some practice problems calculating what it means to be twice as hot. We have the temperature of 0 degrees Celsius. We're going to change it to Kelvin in order to make it twice as hot. So you add 273, and then once you have it in Kelvin you can double it, and doubling the Kelvin temperature would be doubling the kinetic energy, and so you multiply by 2 and you get 546 Kelvin, and then if you want to have the temperature back to Celsius you can subtract 273. So twice as hot as 0 Celsius is 273 degrees Celsius. Now if you wanted 3 times hotter, you would do the same sort of mathematical procedure. You first have to change it to Kelvin, then you can triple the temperature. That would mean 3 times hotter, and again 3 times the kinetic energy, and then if you want to go back to Celsius you can subtract 273. Now if I ask you on a test for 3 times colder, well, you would divide by 3 instead of multiplying by 3. In practice problem number 3 we talk about what phase of water has the highest kinetic energy, and that would be the gas phase since it's at a highest temperature, and the lowest kinetic energy would be ice, which is the lowest temperature. So lowest KE is the lowest temperature. Now in number 4 I ask which has more average kinetic energy, the air in the room, the floor in the room, or neither. They would have the same average kinetic energy, and the answer is C, neither. They have the same average kinetic energy because the air in the room is at the same temperature as the floor in the room. So if they have the same temperature, they have the same average kinetic energy. On the next page, we define what gas pressure is. When a gas particle collides with an object, such as your head or a wall or the walls of a container like inside of a balloon, all those collisions exert small forces on the balloon or on the container or on that object, and the result of all these simultaneous collisions from the billions of gas particles that are in the container causes gas pressure. So all gas pressure is the force of all these collisions. And if you want to measure the pressure, you can use a barometer, and they come in two types. The aneroid barometer uses a gauge to measure how much a column of air in a container is squeezed together by the pressure in the room. And this container is shaped sort of like an accordion. It's able to expand and contract, so there's a little diaphragm that can move up and down as the air pressure changes. And there's a needle attached to this container, and it points to whatever the pressure is. So there's a picture of the aneroid barometer on the next slide, so we'll look at this picture. You can see that there's a vacuum chamber, and this little container is able to expand and contract, and then the pointer moves. On the picture on the right, you see a sealed aneroid barometer. The little cell is able to go up and down as the pressure changes, and then the pointer would move to the higher or lower words on the scale. So that's an aneroid barometer, where a little container expands and contracts. The second type of barometer that is commonly used is called a mercury barometer. It measures the height of a column of mercury, and you can use the millimeter unit, which is a metric unit of pressure, or you can use inches, which is an English unit of pressure. So you're measuring how high up this column of mercury goes inside of a tube. If you want to make a mercury barometer, you're going to have to fill a really tall container that's sort of shaped like a test tube. It's open on one end, closed on the other, and it needs to be about 1 meter long, because the mercury will probably be around 1 meter tall when you make the barometer. But anyway, you have to have a long thin tube, and you have to fill it with mercury, and then you have to have a bowl full of mercury, and then without letting any mercury escape in that long test tube container, you have to flip it upside down in the bowl. Now initially the mercury is so heavy, it's so dense that gravity will pull some of the mercury down, and it's supported by the air pressure in the room, and so the column of mercury initially will fall, so the container won't be completely full. There will be a vacuum at the top. And now what causes the mercury to stay up in the tube is the air pressure in the room. The air pressure pushes down on the bowl of mercury, which pushes up on the column of mercury in the tube. And so as the air pressure changes, as the pressure goes up and down, then the mercury in the tube can move up and down. And the picture of this is on the next slide. The mercury barometer is shown. You can see the bowl of mercury, and you can see this long test tube with the mercury sticking in there. It's pushed up into the tube. Now it's not pushed up all the way, because there's an empty space at the top where some of the mercury ran out. So at sea level, the height of that column is around 760 millimeters tall, and if you go on top of a mountain like Mount Everest, where there's less pressure, then the column of mercury is going to be less tall, so it's only around 253 millimeters of mercury tall. So a unit of pressure can be the height of mercury in this column. Now there are other gas pressure units. The standard metric unit is actually called the Pascal, named after some dead white guy, and the symbol for a Pascal is a PA. Now the standard air pressure at sea level around the Earth is on average around 101.3 kilopascals, which is 1,000 regular old pascals. So 101.3 is our standard conversion factor for pressure in the metric system. So 101.3 kilopascals is standard pressure. There are a lot of other standard pressure units that I have the students know. I give them all the standard pressure units. They don't have to memorize these, but atmospheres is a term for the amount of pressure on a person. So at sea level you have one column of air above you, one atmosphere pressing down on you. As you go higher up, like on a mountaintop, there's less atmosphere above you, so there'd be less atmospheric pressure. So the pressure would be less than 1 atmosphere. Another unit again is the millimeters of mercury. As I mentioned before, it's 760 millimeters tall. If you convert this to inches in the English system, it's around 29.92 inches tall on average at sea level around the world. And then you can also use the unit of pounds per square inch. It's abbreviated PSI, and the students are familiar with PSI when you're airing up your car tires or a bicycle tire. There's a certain number of PSI for a car tire. Well, on average, the standard atmospheric pressure is around 14.7 psi, which means on every square inch of your body there's a force of 14.7 pounds. That's how heavy the column of air is above you. at sea level, there's 14.7 pounds of air pressing down on a square inch of your head. Now, since you're used to this pressure, it's just normal. If this pressure changes, you would sense that in maybe your ears popping, or you're getting a sinus headache or something like that. So we do a practice problem converting from one unit to another, and we did conversion problems in the last chapter, so these one-step conversion problems are very easy. The given is 253 millimeters of mercury pressure on top of a mountain. We're going to change it to units of kPa, which is kilopascals. We use the conversion factor of 760 millimeters on bottom to cancel out with the units of millimeters on top, and we're going to change that to kilopascals, so we use the special number of 101.3, and in one step you get the pressure converted. It's around 33.7 kilopascals of pressure on top of a mountain. If you want to convert it to inches, we start the same process. We write down the given, we put our times line, we put the number on bottom that we want to cancel out with the units of millimeters of mercury. It's still 760 on bottom, but now we're going to use 29.92 inches on top of a ratio because we want to change it to inches of mercury. And so the height of the column of mercury on top of Mount Everest in a mercury barometer would be around 9.96 inches tall. So the pressure is 9.96 inches of mercury. On the next page, we talk about how altitude affects air pressure. I've already alluded to this talking about a mountain. As you go higher up on the mountain, there's less air molecules there, so there's going to be less collisions, or fewer collisions, and so that'll cause less pressure. So the higher up you go, it's less pressure. This is called an inverse relationship, and the graph of an inverse relationship looks like that, as you see on the center of the screen. And the mercury barometer, we had the picture of 760 at sea level, and then on top of a mountain it was like 253. So as you go higher up, there's less air molecules, and so the pressure will drop. Now this is the reason why your ears pop when you go up in elevators that are real quick rising elevators like the Sears Tower in Chicago, or if you go up in planes, your ears will pop, or if you drive up and down large hills in the mountains, you might sense your ears popping, and the ears popping sensation is the air particles trapped in your ear that will expand and contract depending on what the pressure is. Now, if you go deep underwater, you will also feel this increase in pressure, but it's not because of the air pressure, it's the increase of the water pressure. On the next page, I just show some pictures of some demos that I'm going to be doing in class. We crush a can with air pressure, and there's also a large it looks like a turpentine container that gets crushed by air pressure, and I just do these demos in class. And here's a picture of a railroad car that was crushed. They used steam to clean out the inside of this large tank, this large rail car, and then they screwed the top on it while the steam was still in the air inside the container, and when the steam condenses and turns back into a liquid, there's a drop in the pressure, and so every square inch of this container has around 14.7 pounds pressing in on it, and it crushed this rail car. So it's just like the can crushing demo, but on a humongous scale. And there's another photo of it from a different angle. Now we change gears and we talk about the properties of liquids, and so we first introduce a topic called a dynamic equilibrium, and that can be defined as the movement of an equal number of particles back and forth from one state of matter to another. So you have a certain number of particles freezing, at the same time the same number of particles melt, or you have like 5 molecules evaporating as 5 molecules condense. A non-chemistry equilibrium that's dynamic would be like 10 students walk into the room as 10 students leave the room. That would be an equal movement back and forth from one state to another. Now, to be in equilibrium, the rate of one phase change must be equal to the rate of another phase change. So the rate of evaporation must equal the rate of condensation, or the rate of freezing must equal the rate of melting. Now, in an open container, you're not going to reach an equilibrium between evaporating and condensing as shown on the picture on the left. The number of up arrows is 4, that's showing evaporation, and the number of down arrows, which is showing condensing, is only 2. So you don't reach an equilibrium until you put a lid on the container, and once you have a lid on the container, you eventually reach an equilibrium of evaporation and condensation. So the rates of evaporation and condensation are equal. That's called the dynamic equilibrium. Now, the temperature will affect the vapor pressure inside of a container. Now, vapor pressure is simply how much gas is pushing on the surface of the liquid. Now, as the temperature of that liquid increases, so do the number of vapor particles. So you can see the pictures on the bottom. On the left we have low temperature, so there aren't that many vapor molecules above the liquid. At a high temperature, you have more vapor molecules and you have more pressure, as shown by the height of the mercury. So if you have more vapor particles, there's more collisions and therefore there's more pressure, and this is again a direct relationship. If you were to increase the temperature, you increase the number of particles and you increase the pressure. Now, what's this have to do with anything? Well, it relates to why liquids boil. Liquids boil because of a pressure phenomenon, an equilibrium vapor pressure phenomenon. Any liquid will boil when the atmospheric pressure, which is surrounding the liquid, equals the vapor pressure inside the liquid. Now, inside the liquid bubble, there's water vapor, if you're talking about water. So inside water there is a water vapor pressure which pushes out. So as you start to heat a container of water, the vapor pressure of water increases and you get these little bubbles to form. So the image shows the liquid, and then inside the bubble itself that's expanded, you have vapor molecules that keep the shape of the bubble. Now I have another picture of the bubble kind of expanded on the next slide. So before the water gets hot enough, the bubble actually will get squished by the external atmospheric pressure. There's also a little bit of water pressure if the container is really, really deep. But there's the blue lines which represent the water vapor pressure pushing out, and the red lines represent the surrounding pressure, the atmospheric pressure, and again a little bit of water pressure. But the blue lines at the bottom of a container, when you're heating it, let's say on a stove, the blue lines are actually bigger than the red lines, so the bubble is able to keep its shape. But as it travels to the surface, away from the heat source, it gets cooler and cooler, so the blue lines would actually get smaller and the red lines would stay about the same size. And so the water bubble would actually get squished by the external atmospheric pressure if it's not hot enough. Now, once you get the internal water vapor pressure equal to the external air pressure, the bubble can keep its shape and make it all the way to the top surface of the water, and we call that boiling. So in order to get a liquid to boil, you have to make that inside pressure equal to the outside pressure. And there's three ways to do this. The easiest way is just to heat it up. As you heat it up, that raises the vapor pressure inside. Once it gets to 760 millimeters of mercury, you can get the boiling phenomenon. But there's another way to make the water boil without using temperature. You could actually use a vacuum pump. If you surround the water with a vacuum and you suck out all the air pressure, that red line gets smaller and smaller and smaller, that as we had on the previous slide. Now the blue dotted line inside stays the same, and so eventually that red line will get so small that it'll be the same size as the blue. So the internal pressure will eventually equal the external pressure, and then you will get the boiling phenomenon. So you could use a vacuum pump, suck out all the air, and then you'll be able to get the external pressure down low enough that it will be equal to the internal water vapor pressure. And the third way to do it is a little combo. If you lower the air pressure and heat it a little bit, you can get it to boil at a temperature less than 100. So the three pictures down at the bottom shows the water at 70 degrees Celsius. There's an external pressure of 101.3 kilopascals, or 760 millimeters of mercury. There's not enough internal water vapor pressure for it to boil. Once you get the temperature to 100, the external pressure equals the internal pressure. They're both 101.3, so the bubbles can stay as a bubble, and then they break the surface, and we call that boiling. If you're on top of a mountain, since the pressure is only 34 kilopascals, water only needs to get to around 70 degrees Celsius before the internal pressure becomes 34 kilopascals. So the bubbles form sooner, and they're able to make it to the top only at 70 degrees. Now, the normal boiling point of water is 100 degrees Celsius, which means once you get water to 100, the internal pressure is 760, and then it'll bubble. Now, once the liquid is boiling, if you add more heat, it doesn't actually increase the temperature, it just simply produces more bubbles. On top of a mountain, since the pressure is less than 760, water will boil less than 100 degrees Celsius. And because of this, foods will actually take longer to cook when you're on top of a mountain because the boiling water is cooler. And some foods like breads and cakes have special high altitude cooking instructions because of this. Since the liquid inside the bread is at a cooler temperature, you might have to cook it longer, or maybe you'll have to add more water to your recipe or more flour to your recipe. And so there's recipe cookbooks, as we see on the Baking at High Altitudes cookbook that I found online. It's from the Muffin Lady's old-fashioned cookbook. So there's old-fashioned recipes for baking at high altitudes. So water on top of a mountain cooks food slower because it's at a lower pressure, therefore a lower boiling point. Now, you can actually make water boil above 100 degrees Celsius, and you can do that inside of a pressure cooker. And a pressure cooker is just a sealed container, as you see in the picture below. And so because the pressure inside is higher than 760, foods will be cooked in the water that's boiling higher than a temperature of 100 degrees Celsius. So they'll cook faster since the water's hotter. Now, there's actually a phenomenon down on the bottom of the ocean in volcanic vents. They're called black smokers. That's their little nickname. And so the water is next to these volcanic vents, and the temperature is well above 100 degrees Celsius because of all the surrounding water pressure. And so you won't actually have bubbles forming in the water, even though the temperature is much, much, much higher than 100 degrees Celsius. And one other thing about this slide is that, or the little picture of the black smokers, is that there's a lot of organisms that live next to these heat sources for two reasons. One, it's warm, and the second reason is there's a lot of nutrients in the water. And so there's a whole ecosystem around these volcanic vents. And the last little picture that we'll have for this particular part of the lecture, I'm going to break it up into two parts, is an autoclave. An autoclave is used by hospitals and veterinary clinics to sterilize their medical equipment, or to sterilize towels and gauze and whatever they need to use for surgeries. And all it is a closed container, and it has water that boils and it turns into steam, but because the door's closed and the steam can get under high pressure, it gets hotter and hotter and hotter. And so we use an autoclave to sterilize instruments at hospitals. And again, it's just like a pressure cooker. Now, there's a couple practice problems we'll do before we end the lecture. Again, I'll break it up into two parts. The boiling point versus pressure. You can see in this picture, as the vapor pressure increases, so does the temperature. We knew that already. There's a black line at the very top which shows the standard atmospheric pressure of 101.3, and where these lines, the purple, blue, red, and yellow lines, cross the 101.3, that's the temperature that they normally boil. So if you look at water, it crosses right at 100. If you look at ethanoic acid, which is vinegar, it boils at around 120. Ethanol, which is in alcohol or gasoline additives, it boils a little less than 80. And chloroform, which is used as an anesthetic in the olden days to knock people out during surgery, boils at around 60 degrees on a normal atmospheric pressure day. So the normal boiling point for ethanoic acid is 120 degrees. That's where the pressure is normally 101.3. But if you take ethanoic acid up to a mountain, the pressure is only 30. So if you find 30 kilopascals and you read across, the yellow line crosses the 30 kilopascal line only at 80 degrees. So if you go on top of a mountain where the pressure is around 30, then ethanoic acid will boil at 80 degrees. So wherever the vapor pressure equals the atmospheric pressure, that's when it boils. Now the next slide talks about the nature of solids, and we're going to end the lecture here because the chapter basically talks about solids and liquids and gases, and we're only going to do the gases and liquids part first.